So exercise 14 in chapter 14 is asking you how you would make what you would need to buy from some chemical catalog in order to make these different epoxides. And so there are two parts to this. There's one part that's just solving the answer, finding the answer to this, the molecule you need. And that's really straightforward, and I don't think that'll take a lot of time. And then there's an explanation behind that, and that takes a little bit more time to fill in. So let's start with the explanation. There are two ways that you can make epoxides. You can make epoxides with what are called peroxy acids, or you can make them with what are called halohydrons. In both of these cases, you start with an alkene. Remember, an alkene is a carbon chain that has a double bond. So you'd start with that in both of these cases. In the case of a peroxy acid, you'd have some weird carbon chain, and at the end of it, an organic acid, in organic chemistry, the functional group that's most acidic is called a carboxylic acid. It looks like this, and actually, let me just draw that in. So it looks like this. Really, it's an alcohol with a double bond to oxygen on the carbon that has the alcohol. So it's a carboxylic acid, and this can give away this H very easily, so it's acidic. So that would be what this acid is referring to. Now, peroxy, per means a lot. So for example, if something is perfect, it's done completely. It's done a lot, as much as it can be. You can't add anything to it. It's perfect. So something that an acid that is a peroxy acid is going to have a lot of oxygens, oxy. And so you'd take this carboxylic acid, and if you add an extra oxygen in, that becomes a peroxy acid. And so anything that has these three oxygens is a peroxy acid. You may see it written this way, you may see it written with the O's all together, you may see it written even more scrunched up. These all mean the same thing, they're all peroxy acids. The one peroxy acid you want to know about that would not look like this is MCPBA. It stands for meta-chloroperoxybenzoic acid. So MCPBA. Benzene, we know, is that six-membered ring with what looks like alternating single-double bonds. If you have a carboxylic acid coming off of it, so double bond O, and then an OH, that would be benzoic acid. To make it peroxy, so we have benzoic acid. To make it peroxy, we add that extra oxygen in, like we mentioned a second ago. And meta, that just means 3 carbons away. You'll have a chlorine. So 1, 2, 3, here you have that chlorine. The whole big structure for this is not particularly important for us right now. The important thing to remember is that MCPBA is a peroxy acid. So if you see MCPBA, that's going to take an alkene, a double bond, and it's going to turn it in to an epoxide. Now the mechanism for that is not something you'd be responsible for on this test, just in terms of importance and time. So if you had something like this, MCPBA, you would turn that into an epoxide. The mechanism for this is a little weird also, so you can see what's happening. The pi electrons from the double bond attack this oxygen at the same time that the oxygen to oxygen bond breaks. The pi bond steals the hydrogen at the same time that these electrons go to form a new sigma bond. You have this very weird transition state, and you end up with products. So I'm putting this here just because I don't want this mechanism to seem like a magic wand was wafted over an alkene and it turns into an epoxide. But it's something that's complicated enough not to be the priority in this chapter. So, okay, first way to turn alkenes into epoxides is to use peroxy acids. The second way is to use halohydrons. So, halohydrons are molecules that have an alcohol and an alkyl halide, or an halogen, 1 carbon away from each other. You would have learned how to make these in Organic Chemistry 1. You would use some halogen and water, and you would get something like You'd have an alcohol on one carbon, halogen on the other. And you might remember just very quickly how the mechanism for this works. The pi electrons here are nucleophiles, and as this molecule gets close to the bromine is really big. It's really big, so as all this negative charge in this pi bond gets close to the bromine, the electrons in the bromine flee it and go to the other side. That makes that side slightly positive, and here I'm drawing this bromine right here. And the other side is, that makes that side slightly negative. All the electrons are going there, so it's slightly negative. And the other side is slightly positive. That makes this bond want to attack it. So it attacks, it breaks. You get an intermediate, so bromine there, which has a positive charge, and so this is called a Bromonium Ion Intermediate. It's still bromine is still relatively electronegative, so it's still stealing electron density from each of these carbons. So those are still going to be slightly positive. The electrons still want to go to the bromine because the bromine is more electronegative. And so this other bromine, which took its electrons with it, from the bond, has a full negative charge, that will fly away, and you will use the water as the next nucleophile. So you can imagine having this water here, H, and the oxygen is slightly negative here. That attacks this, it breaks this bond. You end up with the bromine kicked open on that one side, and you have the water here. And last but not least, the bromine you had originally swoops back down and steals one of these hydrogens. So I went through this really, really quickly because this is really a review from Organic Chemistry 1. I just wanted to make sure that you would see how you could form this halohydrin. You have a halogen. Hydrogen is referring to the water, which is really the OH, so halohydrin here. Now, once you have this halohydrin, you can do a Williamson ether synthesis. You can take this and add sodium hydride, that really strong base, so that ionic compound that with a metal that gives its electrons to hydrogen, even though hydrogen's not particularly electronegative, and that could steal the hydrogen from this halohydrin. So that would go there. Those electrons would go onto the oxygen, so you'd be left with that alkoxide, so that oxygen with that full negative charge. And from here, you would just do an intramolecular Williamson ether synthesis. The bromine is slightly negative because it pulls the electrons to itself. The carbon it's bonded to is slightly positive. That slightly positive carbon attracts the nucleophilic oxygen here. And that kicks the bromine off. And you get, after all this, your epoxide. So, these were a couple long mechanisms. The mechanisms are not the key thing, although they're both things you would have seen before. This one from Organic Chemistry 1, and this one from the Williamson ether synthesis from this chapter. But the main thing to remember is that your first step in making epoxides from halohydrins is to add this recipe here, and the second step would be to add that sodium hydride. So you have these two ways. Maybe the easier way is just to write MCPBA. And so we can do that in these problems. Now that's the long explanation behind what's happening in this problem, in each of these exercises. But in terms of just doing the exercise, you would take the molecule. So here, we're going to draw this right here. That Me is standing for a methyl group, CH3. Okay, so we have this, and they're asking us, how can we make this? Well, we saw that in both of these cases, ignoring all the other details, in both of these cases, you make the epoxide from an alkene. And the epoxide goes wherever the double bond was. You had a double bond between these carbons, and now you have the epoxide formed on between those carbons. So if we want the epoxide here between the two carbons I'm going to put orange dots on, then those two carbons should have a double bond. And if those had a double bond, all we would have to do is to add either a peroxy acid like MCPBA, or we could also write the reagents for halohydrin formation, followed by the Williamson ether synthesis. Either one of those would be a correct answer. So you could just draw these, and that would be a correct answer, or you could draw these, and that would be a correct answer. Or you could draw both and get a nice big smiley face on your answer. Okay, let's see how that process works in this next one. You want this epoxide with the methyl group coming out at you, hydrogen going away, hydrogen coming out at you, and a cyclohexane ring going away. Notice this is not a benzene because you don't have those alternating single and double bonds. Well, if you want the epoxide to form between these two carbons, that means in your starting material you would want the double bond to be between those two carbons. So that's the carbon chain you would want. If you have that, the halogen will plop, or the epoxide will plop right on top of it to give you your product. So we have that there, and then we just need the reagents to add to this to give us an epoxide. And so we can use a peroxy acid like MCPBA, or we could use the reagents for halohydrin formation, so Br2, H2O, followed by sodium hydride to do that Williamson ether synthesis. All right, how about this one? So we have our epoxide here, methyl group coming out, and we have this quirky ring with another ether in it. So this is the epoxide right here, three-membered ring. How can we form that? Well, wherever that epoxide was, the two carbons that had that epoxide on it are the two carbons that are going to need a double bond, because you make epoxides out of double bonds. And then you would just, and here, let me just make that clearer, and then you would just want to add to that your reagents. So you could either have a strong peroxy acid. Let's use a different one besides MCPBA. Let's use another really common one, which is peroxyacetic acid. And you would recognize that as a peroxy acid because it has all those oxygens there. So that's one way. Or you could just have written MCPBA. Or you can do the halohydrin formation as a first thing, and then followed by sodium hydride to do that Williamson ether synthesis. So if you follow either of those reactions, start here and do this, or start here and do this, in either case, you'll end up with this molecule, which is what the problem is asking you to find or to make. How about with D, last but not least? So this is a pretty big chain. What have we got? 1, 2, 3, 4, 5, 6, just putting numbers in there to keep track. So we have our three-membered ring there. Hydrogen going away, hydrogen coming out at you, carbon going away a carbon, and so here, well, this will be 1. So 2, 3, 4, 5, and 6. Okay, so that's the molecule you want to make. And, oops, with a hydrogen here. And so if you want this epoxide to be right here, what you need to do the epoxide will form wherever you have a double bond, so you would need to make sure that you had a double bond there between those same two carbons. If you have that, the rest of the molecule can stay the same, and you would just want to add a peroxy acid like MCPBA, or the reagents first for halohydrin formation, just like Br2, followed by H2O, and then the sodium hydride, so you get that Williamson ether synthesis. So either of these are possibilities. You could just write this, and that would be a correct answer. Or, if you prefer, you could write that, and that would be a correct answer. So what they gave us in these problems were a whole bunch of epoxides. And what we did is we formed them from two things. We formed them from alkenes. To form those, we just replaced the epoxide with a double bond. Double bond where the two carbons were that the oxygen was attached to. And either with peroxy acids, the most common of which is MCPBA, or the halohydrin formation. And that's how you can make these beautiful epoxides.